So anything in the orthogonal group, and now you saw the yaw pitch roll stuff that I did at the beginning. Guess what? If you study, that was, we started off with a 2x2 matrix, rotations in R2, and so this is the analog of R2. Well, you can do the same sort of deal by making the matrices bigger to generate all of the guys in the generalized orthogonal group. By making these larger square matrices with ones on the diagonals or negative ones is needed. Okay. What this shows really is that, remember we can think of these groups as being somehow geometric shapes, as being manifolds. And I'll show that in particular with the unitary group. That's got a really easy map to show that it's a manifold. But this shows really 1, 2, 3, 4 components. There are 4 sort of separate components to this group of transformations, and they're going to look like this. Okay, and one more. Okay, top and bottom are hyperboloids of, is a hyperboloid of two sheets. These are 2 sheets. And then you've got the hyperboloid of 1 sheet. So I didn't actually work this out and see which is which, but these are actually coordinates. If I take, let's just take this and blow it up. Okay, you get some bowl. Okay, you should think of a bowl. You can actually get really nice coordinates that run on that bowl. That's what these cinches and coches give you, is a coordinate system on one of these planes, or one of these sheets. Okay? And really what's going on, you've got separated components of space. There's no way to do a Lorentz transform and get from certain areas of space-time to other areas of space-time, and we call that causality. Right? You cannot cross the light cone. You can't cross from outside the light cone to somewhere inside the light cone. So these are giving you separate components. If you're outside the light cone, you have to stay outside the light cone. And if you're in the past, maybe you have to stay in the past. I've got to work out the geometry on this. I didn't work it out exactly, but...
Okay, so this group, in other words, this group is the group that takes you 2 points on any of these hyperboloids, right?
Yeah.
I mean...
Yeah, this is what the Lorentz group does.
These are the transforms to go from one point to another. They're like basis vectors in a way. I'm trying to...
Yeah, that's the analog of generators. The analog of basis vectors for vector spaces is generators for groups.
Okay.
So these, if you take, but what you've got to do is take products of these things. You're not really doing linear combinations. You're taking products of these things. But this is like the minimal number of guys from which, if I just take arbitrary products of these dudes, you generate the whole group. Now these are not, well, let's see. These you shouldn't think of these as generators. They're more like the canonical form of the group. So if I have any element in the group, it's going to have some entries, but what I'm telling you is that I can write it. It's going to look like cosh of something, cinch of something, cinch of something, cosh of something,
right,
or
right,
like one of those 4 forms.
Right.
Okay.
Okay.
Now generators, I don't want to talk about that. I haven't thought about it enough, so.
It's okay.
I'll say something wrong. Okay. Any questions about that exercise? What you would be doing? Try it if you get a chance. This is a good way to get your hands on this Lorentz group stuff that I've been railing about, actually, the past couple talks. Okay, let's get... I actually want to start talking a bit about actions right now. And then we'll talk about this picture and how it relates to Lorentz group actions on spacetime. But we'll start off with some simple examples of actions and of course the definition. So. All right, so the definition of a group action. You need a group, and you need a vector space. A group action. And there are other types of actions. You can actually have a group action on a set. But we're just going to look at a group action on a vector space. So a group action of G on V, of the group G on the vector space V, is a map, and I'll call it little dot, from G cross V to V. All right. But this is a binary operation, so let me, all right, we usually write G dot V for when I take dot of G and V. G, V, like this. Okay, so what you're doing essentially, these are all big words that say, I'm going to take a group element and apply it to a vector. And what I get out of the deal by looking at the range must be a vector. Okay. Let's look at an example. Take 1, 2, 3 to be an orthonormal basis for R3. Okay. We talked about the symmetric group, so I can mention the symmetric group. Define the action of the symmetric group S3 on the vector space R3 by this map. G, I'm going to use a sigma for, by sigma of, sigma dot V equals, now I'm going to do a basis expansion of V, sigma dot V I. That's just going to be the sum of VI sigma of VI, which I'm going to define to be E sub sigma of I. Okay, those are symbols. Let's be more concrete. What this says, remember sigma just switches things around. I've got three things. Sigma just switches those three things around.